Hello everyone, welcome to the first lecture of chapter 1, that is the computer system overview. Today we will discuss the basic elements of the computer and see how the microprocessor evolved from early machines to chips we use today. The basic elements of computer are processor, that is the CPU, memory, I/O modules and system bus. These are arranged in this fashion. So the processor mainly contains several registers, and the main task of processor is to control all computer operations, perform data processing, exchange data with the memory, right? We can think of the processor as the safe because it controls all the operations and performs the work and directs others. Okay. Next is the memory module. The memory modules contains several it consists of selection of addressable locations is storing the instructions or data. The memory is just like your kitchen store that holds the ingredients, that is the instructions and or the data. The memory can be of mostly two types. First one is the main memory, which is the RAM. Another is the disk memory, that is the hard disk. As you know, the RAM is fast, volatile and it is temporarily stored, whereas hard disk is slower, non-volatile and it stores the data permanently. Next comes the I/O module. The I/O module. It transfers data between external devices and the processor or the memory. You can think of it just like the waiter. That is, it transfers the order and dishes between the chef and the customer. Over here, it transfers the data between the processor and the memory. Okay, and this I/O modules consist of several temporary buffers for data storage. Next comes the system bus. The system bus provides the communication pathway between the processor, main memory and the I/O. It is just like the corridor that connects everyone so communication can happen smoothly. Now let us dive into the processor registers in detail. What are the different registers available in the processor? Let's now discuss that. Now the processor registers can be some of the registers for your memory exchange. Okay, to exchange between the memory we have basically two registers. First one is memory address register and second one is the memory buffer register. The task of the memory address register is to point to the memory location for data or instruction access. Okay, it will point to the memory location. If you want to transfer the data or instruction, it will point to that specific location, memory location. And the task of the memory of the buffer register is to hold the data that being transferred to or from memory. It holds the actual data which is to be transferred. Likewise, there are some registers for I/O exchange. First one is the I/O address register. Its task is to point to the I/O device addresses. Okay, it will point to the address location of the device from which we need to transfer the data. Okay, and the next one is your I/O buffer register. Its task is to temporarily store data during the I/O operations. Is it clear? Now let's move to the next one, that is the program counter. The task of program counter is to track the address of the next instruction to execute. Okay, it will contain the whole next instruction which will be executed. It increments after each instruction fetch. After fetching one instruction, its address will be automatically incremented by 1. Next comes the instruction register. The job of the instruction register is to hold the instruction currently being executed. Okay, and it is used just for decoding and execution. Means whatever instruction is to be executed, that will be first fetched into the IR. After that, the processor will decode that instruction and then it will execute. Okay, at last comes your execution unit, that is the ALU. Its task is to perform the actual instruction execution. Okay, and it handles mostly the arithmetic, logical, control and data transfer operations. Here actual processing will occur. Now with this, if I think of the analogy, I can say that The MAR is the kitchen label telling which shelf to fetch from. It is just like the kitchen label, okay, means which shelf to fetch it. And the MBR is the tray carrying the ingredients. IOAR tells which customer to serve, which customer to serve. And IOPR holds the plate being served. And the ALU is the chef's hand which is doing the actual cooking task. Okay. Now let's move to the next part, that is the evolution of microprocessors. The microprocessors have evolved through generations. In the first generation, we used the vacuum tubes were used. Those are very large and consume a lot of power. In the second generation, we moved to the transistors, which are smaller, faster, and more reliable. Next, in the third generation, we used the ICs, wherein the multiple transistors are fabricated on a single chip. Next, in the fourth generation, that is in the present days, we are using the microprocessors, the entire CPU on a single chip. It's just like the evolution of a phone, that is from the room-sized telephones to pocket-sized smartphones. Likewise, the computers have evolved. As we move on, the size has decreased drastically. Now, in case of microprocessor, it is mostly it is defined in terms of the word size. Okay, the word size defines the operation of the microprocessor. That is, if it is a 4-bit microprocessor, it means it will handle 4 bits of data at a time. Likewise, now let us see the brief Intel microprocessor history. Initially, the 4-bit microprocessors were developed by Intel. The examples are 404, 4040. This 4 bits microprocessor can handle 4 bits of data at the same time. Next comes the 8-bit. Some of the examples are 8080, the popular one, and 8085. After that, 16-bit processors were developed. The most popular is 8086, 8087. Next comes the 32-bit processor. It contains the Intel Pentium series processors and the dual cores. These are examples of 32-bit processors. And presently, we are using 64-bit processors. Examples are Intel Core 2, i3, i5, i7, i9. These are the 64 bits processors. So I can say that each generation, with the evolution of each generation, it handled more bits of data at the same time. Just like widening a road so that more traffic can flow simultaneously and the speed can increase. Along with this evolution, there are some specialized processors as well, like your DSP processor and GPU, that is graphics processing unit. The DSP are used for streaming audio or video, and often it is used in the modems. Okay, and the graphic GPUs. Okay, in modern days we heavily use GPU for processing for doing the deep learning applications. It is mostly used for gaming, computations, and graphics and parallel computing tasks. I can think of it like the artist of the system painting images on the screens. Okay. So these are the specialized, just like the specialized surgeons in the hospital, while the CPU is the general doctor. DSP and GPUs are expert in their own fields, and the GPU and the CPU will manage it overall. So in this table, this is a brief overview of the different Intel core, the differentiation between the different core i3, i5, i7 and i9 processors. Okay, you can see over here i3, it is good for everyday tasks. It contains 2 to 4 cores. As we move to i5, the number of cores have improved from 4 to 6 and it is used for multitasking and medium workload. Next, if I move to i7, it contains 6 to 8 cores and it has higher performance. Okay, very high performance. And presently i9 processors are also used. It contains around 8 to 24 cores and is used for professional and gaming power gaming type of task, it is mostly you just have a dedicated GPU inside it. So now, okay, so to summarize, we have learned the four elements of the computer, understood the role of CPU, registers. Next, we have explored the evolution of microprocessors from the vacuum tube to the modern Intel processors. And we also saw the specialized processors like the DSP and the GPUs that support specific tasks. In the next lecture, we will see how the processor actually executes the instruction and how the interrupts helped in multitasking effectively. Thank you for watching and see you in the next video. Thank you.